Today's topic is stationary points, and I'll talk about what those are in a minute. Okay, the first thing I want you to do is look at this graph. Can you label anywhere on there where the the gradient is positive, anywhere where the gradient is negative, and anywhere where the gradient is 0? Okay, well actually there's loads of points where the gradient's positive, and if you put a point anywhere along here, then you would have been correct. Or rather, anywhere along here, gradient's going to be positive. Negative is going to be anywhere along here and anywhere along here, because the rise of the run, like it's sloping down all the way. And finally, 0, well, there's just a few points. There's this one, because momentarily, if you were to draw a tangent, you'd get a 0 gradient. Up here as well, because it's changing from positive to negative, it momentarily becomes 0. And there's also a sneaky little one here. It's kind of, although it's positive, it sort of decreases, becomes 0, and then increases again. And these are 3 different types of actually stationary points. So stationary points are where the gradient equals 0. Now, when I say gradient, I mean the instantaneous gradient, of course. So we mean where dy by dx equals 0. And we have another application of using the instantaneous gradient. Taking just another quick look at a graph with stationary points, I am going to give you the names of types of stationary points. So in this situation, and this situation, and this situation, I get the gradient is equal to 0, just temporarily, very momentarily or instantaneously. Well, we call this one a local minimum, okay, because the curve's going down and it comes back up. We call it local because actually it's not the complete minimum, because as you can see from this graph, it later on goes below that. So the word local is important. We call this one a local maximum for similar reasons. And then finally, in this case, we've got the gradient, well, it's positive, it decreases to 0, and then it increases again. So it never actually becomes negative. We call this a point of inflection. So 3 types to be aware of. In future lessons, we're going to classify stationary points into these different types, but not today. The main focus today is just calculating stationary points. Let's look at an example. Find the stationary points of this quadratic, hence sketch the graph, labeling the points and the intersections of the axes. Quite a lot to do here. First of all, let's get the stationary points. And to do that, we need the instantaneous gradient. So we just differentiate. We're going to get dy by dx is 2x plus 4. Now, this is going to equal 0 for stationary points. And I've now created an equation. I can solve it. So I'm going to get x equals minus 2. Now, once I've got that, I've not quite got my stationary point because I need a coordinate. So I need to sub back in for y. Note, I don't sub it back into this dy by dx. That's just going to give me 0 and confirm it's a stationary point. I'm going to sub it back in to here to get my value for y. Y is going to equal minus 2 squared plus 4 times minus 2 minus 5, which is 4 minus 8 minus 5, which gives me minus 9. And I've got my first point that I can just put on my graph. It's going to be down here, minus 2, minus 9. Okay, we've got a bit more to do. We've got to get the y-intercepts and the x-intercepts. So the y-intercept is going to be the next one that's quite quick to get. Yeah, because it asks for the intersections with the axes. and that is going to equal minus 5. It's when x is equal to 0. So I've just substituted 0 into this top one. So I can add that on. It's going to be here. And I might just write minus 5 by it. Okay, I think it's a good idea to do the sketch as we're going along. And then we've got the x-intercepts. Now I know, because it's a positive quadratic, it's going to be one of these. And it's going below the axis. It's definitely going to have 2 roots. So for this, we're going to set y equal to 0. It's going to be x squared plus 4x minus 5 equals 0. Factorize this, x plus 5, x minus 1 equals 0. And x is going to equal 1 or minus 5. And that's going to give me my y values are going to be 0 because I've set y equal to 0. So I'm going to get a point here and over here. And there we go. I've got my quadratic pretty much. Probably best to draw the quadratic first and then put the points in. But there we go. Nicely done. Now the main focus of this was to work out dy by dx. But I also wanted to just linking previous topics. Now you might be saying, hang on, we already know how to get the minimum. We can just complete the square and then we can get the minimum that way. I should have labeled that one. And you'd be right. You could complete the square to get the minimum of minus 2, minus 9. And that means, first of all, you have 2 methods for finding minimums or maximums of quadratics, which is nice. And you might prefer this way. Sometimes in completing the square questions, it will get you to complete the square, and then it will say things like hence or otherwise work out the minimum. And in theory, you could just differentiate and work it out that way. But if you've already completed the square, it would be quicker to do it that way. Now, the advantage, however, is when we're not dealing with quadratics, because although we've got this completing the square method for quadratics, we don't have such a method for ones like the next one, which is a cubic. So my challenge for you now is, having gone through finding the stationary point of a quadratic, can you have a go at this one where I find the stationary point of a cubic? Go for it. Well, I'm going to talk for it now. Dy by dx is going to equal 6x squared. I'm doing this quite quickly now, this dy by dx, but you just got to keep practicing it. Yeah, the constant goes, 24x becomes 24. The others I've multiplied by the power and reduced the power. Now my recommendation is always say this is equal to 0 for stationary points. Don't just set it equal to 0 without given a reason. Okay, now you could stick this into your calculator and solve it, but it is important to have non-calculator techniques as well, so keep practicing that. We look for common factors before we try to factorize, and actually 6 goes into all of these terms, and it's going to work out really nicely. It's going to be x squared minus 5x plus 4. And then this is going to have to, they're both going to have to be negative, because I've got a positive here but a negative here. It's going to be x minus 4, x minus 1, x equals 1 or 4. And at that point, you substitute it back in again, and this is what you get. I'm not even going to talk about this bit. You get 117 and 4 minus 10. Those are your stationary points. This is going to be a positive cubic, and we've actually just found the x equals 1 is going to go with this one, and the x equals 4 and its corresponding y coordinate is going to go with that one, just for info. Okay, let's keep going. What about a quartic? Have a go at this one. Okay, same process. It's going to be 4x cubed minus 16x equals 0 stationary points. Now we've got a cubic to solve. First thing we can do is divide through by the common factor of 4. That's going to make it much nicer. X cubed minus 4x equals 0. Okay, and then actually there's a common factor of x. Now you've got to be really careful. You can't just divide through by x, because actually, I'll show you why in a second. We'll get x squared. If we factorize out the x, we get this, and then we get x minus 2, x plus 2. This is the difference of two squares. So x equals 0, 2, or minus 2. And that is why we can't just divide through by x at this point, because then we'd forget about the solution x equals 0, which does exist. You can see if you put in 0 on the left-hand side for x, you get 0. If you do choose to divide through by x, then you have to account for the fact when x does equal to 0, because you're not allowed to divide by 0. My recommendation is that you factorize it out, but you can write it like this: x squared minus 4 equals 0, or x equals 0, because you've then accounted for the fact that you've divided by it. Okay, and then it's just a case of subbing back in once more. In this case, we get 3 coordinates, and here we are. So this quartic would look, it's a positive quartic, so I think it would look like this, like a little W. These are going to go down further, like quite a bit further maybe, but that's okay. You got the general idea of the shape. Note, not every quartic looks like this. The quartic x to the 4 is simply that. So you won't be guaranteed to get 3 stationary points, but there will be certain conditions on it. In any case, all I'm interested in here is finding the stationary points. I can sub back in. Hope you're happy with this and how this is going. So you're feeling confident with differentiation and finding stationary points, yeah? Quadratics, cubics, quartics? Let's step it up. So what about finding the stationary points of this little function? How do you feel about that? Well, hopefully okay, because we know how to differentiate things like 1 over x. First of all, write it as x to the minus 1. And then it's the same process. dy by dx is bring the power down, minus 1, we can just write that as minus, lower the power, and then this one, 3 times 27 is 81. Okay, not looking that nice, but hey, let's just roll with it. That's going to equal 0 for stationary points. Okay, now my recommendation would be to rewrite it in reciprocal form. So because I've got a minus, I'm going to put the 81x squared first, then it's going to be minus 1 over x squared equals 0. And then there's 2 ways I can do this. I would probably, I like to get rid of the fractions as soon as I can. So I would multiply through by x squared, which, by the way, is absolutely fine in this case. X can never equal 0 here. Like the gradient would be not defined and the function would not be defined. So we're okay, we can just multiply through by x squared. We don't need to account for the fact of when x can equal 0. We're going to get 81x to the 4 minus 1 is equal to 0. 81x to the 4 equals 1. X to the 4 is equal to 1 over 81. You might prefer to do it this way. You might like to set these things equal to one another first and then multiply through by x squared, and then that will take you directly to here. That's absolutely fine. I'm just, I've done it like this way. And then we can work out x by taking the 4th roots of 1 over 81. But in fact, when you take the square root, you need a plus and minus. When you take a cube root, you don't need to worry about the plus and minus. For the 4th root, you are back to needing the plus and minus, because minus 2 all to the power of 4 is the same as 2 to the power of 4. So you've got to account for that. And that's going to actually give us, if you remember your surds, you can take the 4th root of 1, which is just 1, and then the 4th root of 81, which is actually 3. So it becomes 1 over 3, but don't forget the plus and minus in there. Okay, so I've got 2 stationary points. Now I just need to work out my y values, but that's a case of just substituting it in. And in fact, it works out really nicely, and we get a 3rd, 4, and and minus a third minus 4. So not too bad, but trickier, I think, than the other ones we've done so far. Okay, the final question we're going to look at today, the piece de la résistance. This was actually an 8-mark question from an old C1 paper, June 2016, I want to say. Could be wrong. It was the last question in the paper. It tested students on their understanding of stationary points. Give it a go, see how you get on. Okay, I do think that 8 marks on here, getting that is all 8 marks is challenging, but I also think that getting some marks is definitely realistic. Okay, maybe you're like, yeah, 8 marks, easy. Okay, but if not, let's have a look through it. So we're given the curve, but this time we've got an unknown in it. We're told it has a stationary point, and we're asked to find the value of the positive constant a given that the x-coordinate of the stationary point is 32. So we're given some information here. We're not told anything else though. So the first thing I'm going to do is write down my function. Now a over x is actually a times 1 over x. They are the same thing, and so it's ax to the minus 1, but only x is being raised to the power of minus 1 here, and then I add 5. Okay, now I'm given information about the stationary point, the y-coordinate of the stationary point, so it makes sense to find the instantaneous gradients first. That's going to be 8x minus a x to the minus 2. And that is going to equal 0 for the stationary points. And although I can't solve this for x because I don't know what a is, I can still make some progress. I can say that 8x is going to equal a over x squared. I've added this to both sides and then I've written it in its reciprocal form. At this point, I could work out x in terms of a. However, it actually makes more sense. That's going to involve a cube root, so it makes more sense to write it as a is equal to 8x cubed. And I have a relationship between a and x. That's the main thing. Now, I'm told that the y-coordinate of the stationary points is 32. So, I know when a is equal to 8x cubed, because that's the relationship at the stationary point, y is equal to 32. And this is what I can do. I can actually substitute in to this equation here. It's going to be 32 is 4x squared plus a, but now I can use this condition because I'm talking about the stationary point. Maybe I should write that at the stationary point this is true. I haven't quite finished yet. Over x plus 5. And what I've done is now I've got an equation with just one unknown. These are going to cancel to give me 4x squared plus 8x squared. What I can do is I can minus 5 from both sides, add these up, I've got myself an equation. And that's going to mean that x squared is equal to 27 over 12. Now I'm going to do this non-calculator. Actually, the original paper was non-calculator. I can cancel this down. It's going to become 9 over 4 if I divide through by 3, and therefore x is going to equal the square root of 9 over 4, plus and minus, don't forget, which is actually plus and minus 3 over 2. And we've worked out the x value of the stationary point. Brilliant. Now I can work out a. So a, now actually I only want the positive value of a, so a is going to equal 8 times 3 over 2 cubed, ignore the negative one, and that's going to be 8 times 27 over 8, and we are done. A is equal to 27. So lots going on there, okay? But we rolled with it. We did dy by dx. We got a relationship, and then we used all the information we had, which was this information here, and the fact that the y value is 32. We used the original equation. We solved for x, and then we worked out a. Just very quickly, there is another way we could have done it, and this might be the way that you would have naturally have done it. Okay, and that is to rearrange this one here. So I could have written down that x cubed is equal to a over 8, and then cube rooted to give me a to the third over 2, because I cube root the a and I cube root the 8. And at that point, I could have substituted into this equation. Okay, and I would have got 32 equals 4, and then I would have had to have squared the x, so that would have been a to the 2 over 3 over 4 plus a over x, so it would have been a over a to the third over 2, and then plus 5. And what I would have got is an equation involving a with a fractional index rather. I could have solved this. Do you know what? I think I'll keep going. Why not? Sorry, it's becoming a little bit messy now, but if there's a bit of space here, so then I would write down 32 equals a to the 2/3, because these 4's cancel, and this would become 2a to the 2/3, because it would be a times 2 over a to the third if I change the division round, and then I'm adding 5, so I'd get 27 equals 3a to the 2/3. A to the 2/3 equals 9, and now I've got fractional indices that I can solve, because this is going to be a squared cube rooted equals 9. Actually, I don't want to write it that way around. It's better to write it as the cube root of a squared equals 9. So that would mean the cube root of a would equal 3. I can ignore the minus 3. And finally, I can cube that and get 27. Now, I think that might be a more natural way of doing it, to get x in terms of a and sub it in. I think it's harder though. You know, there's a lot more errors that you can make, but it's maybe more intuitive than substituting in for a. So I just wanted to talk about those two methods for solving it. I hope that question makes sense.